our final topic in this chapter, we're going to be talking about Le Chatelier's principle. And this is what I was kind of alluding to in class when I was foreshadowing with the light bulb demo. Okay, so Le Chatelier's principle says if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. So there are several things, several changes we could impose at equilibrium. And the first one we'll talk about is concentration. And this has the same effect as what we have been kind of talking about with the reaction quotient. Okay, so for example, if a system has too much reactant, it has to shift to the right. If a system has too much product, it has to shift to the left. Okay, so let's suppose we're at equilibrium and we add more product. Well, if we're at equilibrium and we add more product, then our system is going to have to shift back this way. Okay, so what if we're at equilibrium and we add more reactant? Well, now our system has too much reactant, so it's going to have to shift back this way. Okay, so now what if we're at equilibrium and we take away reactant? Okay, so if we're at equilibrium and we take away reactant, it's as if our system has too much product and it will shift back to the left. Okay, so we'll say add product. Here we'll say remove reactant. Here we'll say add reactant. And then finally, as you might guess, if we're at equilibrium and we take away some of that product, then now it's as if our system has too much reactant. Okay, so it'll want to shift back to the right. So that would be like if we removed, so minus product. And there's a number of ways we can achieve these things by adding product or removing product, adding reactant or removing reactant. But all the same, we want to recognize that when we do one of these four things, the system is going to shift back to its equilibrium position. Okay, so what about if we change the pressure of the system? And we can do that by adding or removing a gaseous reactant or product. Okay, that's the same as concentration. So if we add pressure in the form of a reactant, it's going to shift to the right. If we add pressure in the form of the product, it's going to shift to the left. If I remove pressure in the form of a reactant, it's going to shift left. And if I remove pressure in the form of a product, it's going to shift to the right. Okay, so what about adding an inert gas not involved in the reaction at all? No change. So if we add, let's say, like some inert gas that's not involved in the reaction, it increases the pressure of the system. But if that gas is not involved in the reaction, it doesn't affect the equilibrium position. Okay? Now, what happens if we change the volume of the container? Well, I have another slide for this, but what we need to remember, concentration is mole per liter. So when we change the volume of our container, we are going to be changing the concentration, and the equilibrium position will have to change accordingly. Now, this one can get confusing, this volume thing. So there's an easy way to remember this, okay? And so what we do for that, oops, let's see here. I flicked my mouse hot corner by accident. Okay, we're back. So there's an easy way to get this volume change correct. And that is when we balance our reaction. So for example, I'm back to this Haber-Bosch reaction. We want to keep track of the total number of molecules on one side and the total number of molecules on the other side. So total on this side and total on this side, okay? And so now what ends up happening is if I increase the volume of this system, so remember this is mole per liter. So if I'm increasing the volume, that has the effect of decreasing the concentration. And to compensate for that, the system is going to want to shift to the larger concentration of molecules so that the concentration is preserved, right? So if I increase the volume, I make the liters bigger, then I also have to make the moles bigger. And so for this particular reaction, right, this is reaction specific. For this reaction, it's going to want to shift it back to the reactants because if the volume increases, the number of moles have to increase, and there's more moles on this side, 4 versus 2, so it has to shift that way. Okay. So now similarly, if I decrease the volume in this reaction, so I am decreasing the volume, which means that I need to decrease the number of moles correspondingly. And so because there's 2 molecules on the right side and 4 molecules on the left side, for this decrease in volume, that's going to have to shift it to the right. Okay. So again, this is reaction specific. And when we're thinking about these volume changes, we need to first consider the total number of moles or the total number of molecules on the corresponding side. Okay. And so this is kind of a pictorially showing you what's going on. So we can imagine if we had some type of piston where we either expanded it or compressed it, we're going to see equilibrium change in this system as a result of changing the volume of that piston. Okay. And so the last effect we'll talk about is temperature. And look, this is important. This is the only effect that actually changes the equilibrium constant. So those other things, concentration, volume, pressure, they change the position. And what that means by changing the position is the amount of reactants and products will shift to either the left or the right, but it preserves the equilibrium constant. Temperature, however, will actually change the value of the equilibrium constant. So that's why you've seen in all of our sample problems, it says, the equilibrium constant is 115 at 700 Kelvin or whatever. Because for that same reaction at a different temperature, the equilibrium constant will have a different value. Okay, so let's describe this. So there's 2 scenarios when we have an endothermic reaction and an exothermic reaction. And so hopefully you remember in an endothermic reaction, energy is a reactant. So in an endothermic reaction, we have to put energy in as a reactant. Okay. And so what that means now, if I increase the temperature, it's like I'm adding more energy, right? And it's that same effect. If I'm adding more energy to this reaction, to this endothermic reaction, that's going to shift it to the right. So that's going to allow more products to form. And disproportionately, it's going to increase the value of K. All right. So for endothermic reactions, increasing the temperature increases the equilibrium constant and shifts the reaction to the right, meaning it makes more products. Okay. So, and now for decreasing the temperature for an endothermic reaction, it's just the opposite. So when I decrease the temperature, it's like I'm taking energy away, and that means not as much products can form. So it shifts the position to the left. So there's more reactants. So that means the position is at the left, and it decreases the equilibrium constant. Okay, so what about for an exothermic reaction? Well, recall on an exothermic reaction, energy is a product. Energy is released in this reaction. Okay, so if I increase the temperature, it's like I'm adding more product, and that's going to want to make this reaction go backwards. It's going to want to make it shift to the left. And so that means the equilibrium constant gets smaller. Okay, so just the opposite of the endothermic case. And then similarly, in an exothermic reaction, if I decrease the temperature, it's as if I'm taking away some of the product. So now the reactant wants to fill in that empty space, and I shift this reaction to the right. And there's actually some really cool application to this last case here. So little did you know, combustion reactions are actually far more efficient when it's colder. I'll say that again. So when we have a combustion reaction, like a fire or an explosion or something, right? Energy is a product, okay? So if you do those types of reactions at a colder temperature, those reactants will turn over to products more efficiently. So combustion works better when it's colder outside. I know that seems counterintuitive, but it's because it's so cold, there's less energy to fill in. So those reactants want to push over to products even more to fill in that empty space. Okay, and so the very last thing we'll do, here's a number of examples. Okay, so we've got a simple reaction here. The decomposition of N2O4 to make 2 NO2s. All right, we can see delta H for this reaction is positive 58 kilojoules. So that's an endothermic reaction. And now let's think about what all these things do. Okay, so if I'm at equilibrium and I add more N2O4, so if I add more reactant, it's going to want to shift to the right. So shifting to the right means it makes more NO2. Okay, so what if I add more NO2? Well, if I add more NO2, it's going to shift to the left, so it's going to want to make more N2O4. Okay, so what if I remove N2O4? Well, if I remove N2O4, now there's not enough reactant, and so this product is going to want to shift back to the left to fill in that N2O4 that I removed. And similarly, if I remove NO2, this N2O4 is going to want to shift in a way that fills in that missing NO2 that was removed. Okay, so what if I add helium to this reaction? Okay, nothing. We'll just say not applicable, no change, because helium's not involved in this reaction. It doesn't change anything at all. Okay, so now here's all these decreased container volume. So remember, we've got 2 molecules here and 1 molecule here. So if I decrease the container volume, then my number of moles also needs to decrease. And so that means I got to shift to the side that has less molecules. So in this case, it's going to be to the left. And if I increase the container volume, I need to increase the number of moles. So it's going to shift to the side that has more moles. So that means in this reaction, it's going to shift to the right. Okay, what if I increase the temperature? Well, this reaction was endothermic. Okay, so if I increase the temperature, I'm adding more energy to it, so it can shift to make more products. So that's a shift to the right. And similarly, if I decrease the temperature on this endothermic reaction, it's going to shift to the left. Okay, folks, so that was a little fast whirlwind through this last video. We'll do plenty of examples in our live lecture meeting. And this concludes Chapter 14. Hasta luego.